Hello everyone, my name is Zhang Shuhan, and now I will introduce the method that I use to solve the question 1 of homework 10. The question 1 asks us to find and collect the simple properties of 1 to 7. The first is Poisson process, and second is Poisson increment process, and the third is Poisson impulses. The fourth is semi-random telegraph signal. The fifth is random telegraph signals. The sixth is random walk, and finally is Wiener process. First, we will discuss the Poisson process, which is also called Poisson counting process, and it is defined by the following properties. First, the number we denote it as n t1 t2, and t1 t2 is a time interval, and we also denote the t equals to t2 minus t1. This is and the Poisson random variable with parameter lambda t, and we write the probability dense functions like p n equals to k equals to e to the power of minus lambda t and time lambda t to the power of k divide the exclamation k. If the interval and second, if the interval t1, t2, and t3, t4 are non-overlapping, then the random variable n t1, t2, and n t3, t4 are independent. The third is at a time moment t, there is no more one Poisson point. Using the point ti, we form the stochastic process big xt equals to n0t. And we can draw the stochastic process like this. And this is one sample. We can have different ti. And then we write the first order probability mass equals to also has same functions of Poisson random variable. And the mean of xt equals to lambda t, and autocorrelation of this stochastic process equals to lambda square t1, t2 plus lambda times meaning of t1, t2, and the autocovariance is equals to lambda times minimal t1 and t2. And furthermore, we discussed this process a little bit. The mean of Poisson process with lambda t, which is a linear function of t, it matches our common sense. The longer time we wait for, the expected number of buses is larger. Then the autocorrelation functions contain a term of minimal t1 and t2, which comes from the property of independent increment. The second, we need to write the property of Poisson increment process, and it is defined as big yt equals to xt plus epsilon minus xt and divide the small variance epsilon t, where the xt is Poisson process. The first order probability mass functions should equals to this. It also has the same expressions like Poisson distribution, and the mean of big yt should equals to lambda t, and the autocorrelation, and then the autocovariance. And then we discuss these properties a little bit. First, the Poisson increment process is introduced to prepare us to define Poisson impulse process. And it is interesting to see that in the expression of autocorrelation, like this, is a triangle when area lambda, which is independent of epsilon. When epsilon goes to 0, the triangle becomes an impulse with area lambda. Then we will introduce the Poisson impulse process, which is defined as big ZT. We can draw the graph of big ZT, and at each time ti we have impulse functions. So we don't have probability mass functions because the impulse functions doesn't has the mass functions. And then the mean of zt equals to lambda, and the autocorrelations equals to lambda squared plus lambda time delta t1 minus t2, and autocovariance equals to lambda delta t1 minus t2. And we discussed this. First, the process, as we can see, the excitation of zt equals to lambda, so the excitation of zt minus lambda should equals to 0, and the autocorrelation of this will the autocorrelation of zt minus lambda should equals to lambda time delta t1 t2. So that is zt minus lambda is a white noise, and because the autocorrelation is purely random. In the real world, when there are some short noise as this figure below, because in the real time we couldn't have the event with time interval nearly to 0. It always has some time intervals. So the impulse in real world should like this graph. And next we will talk about the semi-random telegraph signals. And xt is based on the person point again, and the number of nt1 t2 of point ti in the interval of t1 t2 of lines t equals to t2 minus t1 is a Poisson random variable with parameter lambda t, and the excitation and the functions of this probability mass functions is has the same expression like Poisson distribution. And we define the stochastic process big xt equals to 1 when the number in the time interval 0 to t is even, and big xt equals to minus 1 when k is odd in the time interval of t equals to 1 to t. And the first order probability mass functions of this stochastic process when big xt equals to 1 should equals to this, and the probability of big xt equals to minus 1 is equals to this one, and the mean of big xt should equals to the e to the power of minus 2 time lambda time t. So the autocorrelation and the autocovariance can be expressed as this. So we discussed these properties a little bit, and we have the probability of big xt equals to 1 is not equals to 1 over 2, because we start with 1, not 0, and the probability of big xt equals to 1 should be a little higher than 1 over 2, and the so that's why we have these expressions. And this expression goes to 1 over 2 when t goes to infinite, which matches our expression. Which matches our expectation. The expectation of big xt should equals to e to the power of 2 lambda t goes to 0 when t go to infinite, which matches our expectation as well. The autocorrelation goes to 0 when t1 minus t2 go to infinite. That matches our common size. When t1 and t2 are far away, the big xt and big xt1 and big xt2 are less correlated, because they are has more probability to be independent. And what's next? We are going to discuss the random telegraph signals big yt equals to a times big xt. And the probability of a equals to 1 equals to the probability of a equals to minus 1 equals to 1 over 2, which we can define this as a fire cone. And where xt is semi-random telegraph signals, like we discussed above. And the first order of probability mass functions are p big yt equals to 1 should equals to the p of big yt equals to minus 1 and equals to 1 over 2. And the proof is pretty easy. We just apply the probability of big xt and the probability of a equals to 1 and minus 1 to these expressions, and we get this final result. And expectation of big YT equals 0, and the autocorrelation and autocovariance should equals to this. And furthermore, we have the probability of big YT equals to 1 equals to the probability of big YT equals to minus 1 equals to 1 over 2. This makes us guess that YT, the big YT, may be strict sense stationary, because the big expectation of big YT equals to constant also make us guess SSS probability, SSS property. Next, we are going to talk about random walk. Let's we toss a fire coin n times, and we have the heads k times, and the tails equals to n minus k times. So we have the big xt, which is a stochastic process, and equals to the number of head minus the number of tails, and multiple s. S is a step. We have this big X nt equals to 2k minus n times s. And we are going to talk about the first order probability masses. The probability of big xt equals to rs equals to select m plus r divided 2 out of n times times to the 1 over 2 the power of n. And the expectation of big xt should equals to 0 because it's a fair coin, and the autocorrelation equals to the minimum of nm times s square, and autocorrelation equals to the minimum of n and m, and multiply s square. We are going to talk about this a little more. First, from the probability mass functions, we guess that when the n goes to infinite, we will have Gaussian density, and the autocorrelation functions contain a term of minimal T1, T2, which comes from the property of independent increment. And finally, we are going to talk about the Wiener process, which is also called Brownian motion. Big Wt equals to limit big xt when big T close to 0 and s close to 0 and n going to the infinite, and the portion of s square divided t should equals to alpha, and alpha is a constant, and we call this process like random walk. The first order density functions of fwt should equals to this, and which has the similar expression of normal distribution, and the mean of big Wt equals 0, and the autocorrelation should equals to the minimum of T1, T2 times alpha, and the autocovariance of this process should equals to the minimum of T1, T2 and times alpha. So that's all. Thank you.